let's talk about a pragmatic guide for data movement. And we know it's been there for over 20 years. There are a lot of old dogs and also new tricks. So let's navigate through this landscape and see where we can build for like modern data movement platform. So a little bit about myself. I'm a founding engineer at Decodable. So in fact, Decodable is a startup doing real-time data movement, and we run our product on top of Apache Flink. So I joined as a software engineer. In fact, I wear a lot of hats. Currently, I'm managing the product. Sometimes I do solution architects for our prospects and customers, and also do post-sales customer support. So lots of things to do. I think it's a kind of exciting and also tiring job if you want to know what startup is like. So for today's agenda, we want to talk about where is data movement, and we'll talk about all kinds of data movement patterns, and I'll present our view of what a unified approach to data movement look like. So in short, data movement is everywhere. So I'm just putting like a simple diagrams here that show you a typical business. And of course, in reality, it's more complicated here than this diagram. But typically, you have an operational side of the system where your services run, serve your customers. There's a bunch of data systems backing the services. Typically, the first database you will introduce is a relational database where you store the data serving the applications. And there will be, once you have more customers, you start introducing cache to accelerate some lookup for specific information for better user experience. And typically, you would also introduce the search database document store to accelerate the search for text search. And of course, you would monitor your services. So there's some logs and metrics collected, allow you to send them to the monitoring system to monitor your services, make sure it's running. With business growth, we all know it's important to make data-driven decisions. So normally, operational database is not a good place for that. So some data movement happens, starting moving the data from the operational data systems to the analytical data systems. So typically, data warehouse like Snowflake, or data lakes like Iceberg or Delta Lake. And after that, you can also, it's very trendy to study like training ML models. So you normally typically have a feature store that's in the analytical data systems plane. So traditionally, the data movement from operational database to analytical plane is through batch processing. So Spark and Fivetran are very popular systems there. So even in this diagram, you can see data is moving from application to like 3 operational data stores. Logs and metrics gets moved to observability systems. And you see the data from the operational data systems to analytical data systems. So it's just everywhere. The data is moving all the time through different systems. So as I said, this is just a recap of what we just said. And I use slightly different terms here for online and offline. Online is basically whatever use cases that's serving your business. So you know, like this real-time analytics summit, a big thing is user-facing analytics. That's also in the online system. Cache index I already covered, and observability. Offline, where you do data analytics, business intelligence, ML model training. So let's keep going. Typically, how do we move data? This is the traditional way. So this belongs to the ODocs section. We do batch ETL. ETL stands for extract, transform, and load. And sometimes we shift these last two letters. We do extract, load, and transform. And of course, for all those direct links I show you from like application to the operational data systems, those are point-to-point. This is the most sneaky one where people don't think it's data movement, but it still actually is. Think from event-driven perspective, an event happens and that data gets moved into like a cache or search index in some way. So those, in our view, all belong to data movement. And now I'm going to talk about the pros and cons for each of the systems. Just to show you where the batch ETL is, so that's usually from data movement from the operational data systems to analytical data systems. Spark is the most popular one there. You can also do apply transformations while the data movement happens. So the main thing for batch means it runs data movement at a predefined schedule. Over the years, this has become way better than before. Many years ago, people usually run this as a nightly job. That's a thing. Now this can be run like hourly or even within maybe 10 minutes, depending on how much data volume you have, and also how complex the transform is. So in terms of pros and cons, so the good thing is this is a well-known pattern. It's been there for years, and the systems are pretty robust. The downside, as you can already realize, because it runs on a predefined schedule, there's always going to be scheduling overhead, and also the whole system is just designed to move batch data. So it's not very suitable for online use cases. In fact, I've never seen people use Spark to populate cache index. There might be, but I don't know. Okay, so ELT is basically loads data first into the system and apply transformation inside the data system. You probably have heard about like the modern data stack. That's basically the whole idea is you have all this data, you replicate, and Fivetran is part of it. You replicate the data and put it into a data warehouse like Snowflake, and then you can apply transformation after data lands inside Snowflake. The pros and cons about this is it's super simple to use. And here I'm specifically talking about data movement part, right? Like that basically means we are taking away the T and the system becomes so much easier. It's basically data replication. So it's that pushes the complexity of T outside the data movement to a different system. So it's very simple to use, but again, this usually traditionally is designed in running batch, so it's not a good use for online use cases. And also this means the data in the destination system must support transformation, and that's one of the restrictions. So if you put that into a system like a cache doesn't support joins, so that's one of the drawback. And also sometimes for security and compliance reasons, you can't have data stored in your system with PII. So if you just have a system doing data replication without any transformation, that's not a good use here. Let's keep going. So, and now let's look at all those point-to-point cases, as I mentioned. That basically means you have direct data connectivity between where the data is generated and where the target system is. And you can apply custom logics there however you want. So the good part of this is it's super specialized for the specific use case. So you have the most information and flexibility to optimize for the use case. If it is online, then optimize for online. If it is offline, then optimize for offline. Your data volume is high, optimize for performance. Your data volume is low, maybe optimize for cost, depending on your specific use case. The downside, actually not downside, it's just a limitation is it just feels there's a lack of abstraction And sometimes when there's a lot of data movement happening, there can be data inconsistency issues. I actually wrote a blog about it, so if you want to learn more about it, you can look at it. In short, when I say data inconsistency issues is, remember this diagram. So you can see the application needs to keep the operational database, cache, and search in sync. So that means if I want to issue an update, I need to update 3 systems. So what you want is this operation to be atomic. It's either all 3 systems get updated or none. So this usually requires distributed transaction. And trust me, it's actually not as easy. There's a lot of research in this area, but it's not, even now, it's not easy to handle. There's a lot of code around it to handle a specific use case. You need to handle like partial failure or that kind of stuff. So, so normally, it's just one of the things to consider. Okay, so far we talk about all those traditional technologies, and here at Real-Time Data Analytics Summit, I know we all know a lot of like real-time technologies. So I'm going to quickly go through some of the new tricks here in for data movement. So change data capture, CDC, and I'll talk about event streaming and stream processing. So maybe we show up ahead. Who are the people who know all 3 of this? Okay, nice. I know it. You all know about this, at least heard of it already. So change data capture basically captures database change events in real time. So it turns what happens to the database into events. And the idea is then you get a stream of change events. You can have your target system to react to those events in real time. So I actually have an example here for each of the new tricks. So this is Debezium. Debezium is an open source project for change data capture implementation. It's a log-based change data capture. If you wonder, there's another way of doing change data capture. It's trigger-based. In my view, of course, I choose to use Debezium and decodable. So I prefer log-based change data capture. So this is basically a quick diagram showing you any changes to the database. So you run your DML, inserts, updates, or deletes. That becomes a list of events that ends up in the transaction log with a bunch of events. And that's basically the change events. And the Debezium is a separate process that keeps reading the transaction log and capture those events and emit the change events into the target systems. So the core part of this is it enables real-time data movement. So it's a good candidate. It makes online use cases possible because the target system can just react to those changes. The limitation here is change data capture itself doesn't do anything. It's just a stream of change events. You need the integration of taking actions on those change events. So either it's putting into a different system, or you want to write a microservice or applications. That's additional stuff you need to handle. And the next one is event streaming. So it's basically the event streaming is it allows real-time event ingestion into a persistent storage. It's usually message queue, so you can you put the events into a persistent event queue, and this also allows decoupled event consumers to consume those events in real time, but in a decoupled way. So let me give you an example. So in terms of Kafka here, you can have multiple producers that are independently putting data into different topics. And you can also have decoupled consumers. They manage their own state and to consume the events that's in the topics. So this is a very decoupled design that makes a lot of use cases possible. And the whole system is designed to provide low latency. So let's talk about the pros and cons. Again, like this is event streaming is designed for event-driven architecture. So it supports low latency use cases like online use cases. And because it's persistent queue, you can source the data once and the consumers are decoupled. You can consume multiple times at the same time or even at a later time. The limitation here is such systems doesn't have a lot of processing capabilities. So in terms of Kafka itself can do some single message transfer. So that means it can do some transformations for each message, each event. But if you want to look at some events as a whole, for example, you are computing a count of the messages or like looking at some events, doing some aggregation over a time window, it's limited. And Kafka itself cannot do that. And in such cases, additional infrastructure would be needed. Last but not least is stream processing. And I have a lot of words to talk about here. I've been spending my past 6 years doing stream processing. At the core, stream processing provides the continuous and incremental processing over streaming data. So in this diagram, you can see it continues as the message is coming to the stream processing engine. It updates its internal model and emits the results in real time per event. And an example of this is Apache Flink. This is so far the most popular and bystander for stream processing. It's built in a way that's highly scalable. And it's built to do complex stream processing. So where the data accuracy and consistency is super important, and it's at the core, it supports exactly once delivery. Also on top of it, it has different APIs for different use cases. So it has a SQL layer that's super easy to write the transformation logic, and it has data stream API that's language specific. You can do it in Java or Flink, or Python that give you more expressive APIs to write to apply your transformation logic. And this technology is very commonly used in, I think people heard about it all the time, fraud detection or like real-time monitoring. So the good part of this is, of course, it supports online use cases, and it supports really complex transformations and still maintaining the low latency for computing the results. The limitation, or is a common understanding, is running Flink is very difficult because it's a distributed system and it maintains internal state. So anything that requires handle failure with a state is not as easy as any stateless services. So operation story is really a challenge for running Flink. So far we talk about all those technologies. What's the conclusion here? One thing I talk about it, but I didn't say it out loud, is the data stack is always heterogeneous. So you always have different systems for specific use case. There's a cache, and there's a relational database, there's a search document store, there's a feature store, data lake. I don't really see any company who can just run their whole business with one database. Even if you start with it, as a company grows, as a business grows, there will always be more specialized data stores added to the data stack. And for all of the data movement technologies or patterns we talk about, they have their different trade-offs. So whether that's easier to use than at the cost of not being able to do transformation, or it's super fast, but it's very hard to operationalize. There's always a trade-off. And of course, the newer patterns always focus on online use cases. And this is kind of easy to use as the business grows. We always want fresher data to make the best decisions, and supporting real-time data movement is harder than supporting batch movement. So newer ones, of course, we are pushing the edges there to be able to offer the low latency use cases. So for the next section, I want to talk about, okay, with all those technologies, how do we choose? And this is a wall of text I don't meant for you to read. The thing is, me as an engineer, whenever I'm adding a system and I need to move data, I need to make some decisions about, okay, now I need to have a new system. I need to move data from system A to B. What that system is, where does it need to go? What is the latency requirement? What are the flexibilities I have? What are the existing tools I have? So there's always a lot of things going through in the head, and eventually you end up having like multiple movement tools because the decision is also made by different people at a different time. So you end up having a lot of data movement tools in-house. So what about if we have a unified data movement platform that everyone can just plug in and get what they want? You kind of want like how you connect your internet cable. You don't care about the implementation there. Data just start moving. You don't need to care about internally how that gets moved. I think that's a good idea, and that's what Decodable is trying to build. But I know whenever we talk about unified, it kind of sounds like sales and marketing words. So I definitely see some people thinking about, oh, when you see a unified data movement, data platform, is that just like a bunch of tools and you can pick and choose? I just give you one invoice. And that is not what we are talking about. So in our thinking, there are a few things that a unified data movement platform should offer. So it should abstract away the underlying technologies. Again, think about maybe another analogy, like you plug in a cable, not power charge. You don't care that power is from water, nuclear power, or windmill. It just gives you the power. So you kind of don't want to let the user choose what technologies to use for data movement. It should automatically choose the most appropriate technologies for you, and you shouldn't need to switch to a different platform just because you want to do a different data movement. So that's the guiding principles for data movement. Well, those are what we think it should. The guiding principles for us is, since we talk about all those systems that support online use cases, and online, the main difference is lower latency. So by default, real-time or online use cases also cover the whole range of offline use cases, because you just have, like, who doesn't want fresher data? And another principle is we want one-to-N connectivity. So think about it. If you have a database, you want to move that data to a few different systems because that powers different use cases. You don't want to put in a lot more load every time you need to move that data. You want to source it once and consume it multiple times. So the connectivity needs to be one-to-N. And in our view, ETL is greater than ELT because it just offers more capability, and that T can be optional, and that basically becomes the ELT. So in this way, ETL is the superset of ELT. And of course, when we say unified, it's not just putting things together. We need a unified user experience. And let me show you for each line what I mean. So here is a data platform. We have basically what's happening under the hood. You can probably see we use all the technologies I just mentioned, CDC, streaming systems, and stream processing. So you can basically move data in real time through the whole stack from left to right, whether it's application, data store, to online use cases for search, cache, or offline use cases for data warehouse, data lake, or feature store. So real time is the default. And for one-to-N connectivity, this is where we talk about Kafka or streaming systems offers decoupled producers and the consumers. So moving the data to Kafka first, and then you can have multiple consumers to power different systems. So you can see like, if I need to power both search and cache, I just need a separate connection to Kafka rather than putting that load into the source database system. And for ETL greater than ELT, again, the whole thing is T should be possible, but not necessary. So as I showed the design we have, actually here, you can see all the systems, the connections are interacting with Kafka or the streaming system. So that makes the interface really easy because they all work with streaming data. So in this way, basically, E on the left side, extracting the side, transform load, they all interface with streaming data. So you can apply transform data when needed. That basically means if you don't want transform data, that T doesn't exist. You just don't need to use it. And there's no additional cost or latency when it's not. And in terms of unified UX, this is where the abstraction comes in. Users shouldn't think about all those different systems. When they do data movement, they just think about applying a source and applying some transformation and applying the sink, if needed for transformation, of course. But under the hood, the model would, for the source connector, it would turn all the data into a uniformed streaming data. And the stream processing would continuously process the streaming data. Sink connectors would consume the streaming data, and put them into the destination systems. So it's a very simple model to understand. But unified UX is not just about model. The way to think about it is you should be able to write different data movement jobs in a unified way. So here's only a snippet, but our approach to this is you can write declarative YAML for ELT or ETL, SQL processing or language-specific processing. You use the same declarative YAML for online or offline use cases. So everything stays the same. It's the same type of experience. So in summary, I talk about this. Data movement to us is a stubborn problem. It's been there for 20 years, lots of tools. It's still a problem that everyone has. For us, a unified data movement, it should feel like a Kubernetes for movement. Think about when you used to deploy applications. There are different systems, different ways of different servers, different data centers, just different specialized code to manage just the deployment part of the services. Once Kubernetes unifies all that, now everyone just needs to learn Kubernetes, but you still have the flexibility of using it inside the data center or AWS or GCP. So that's where we think data movement is. It should abstract away the underlying technologies, but still stay flexible to use various of technologies. Okay, so that's the end of my presentation. It's a Q&A time, and I also put my QR code if you want to follow me on LinkedIn.
My question was about data movement and monetization of data. So is there anything in the works now or currently supported where you can support data sharing, but controlling access and making sure usage is restricted? Like people can't copy your data, but they can still use it and do analytics on it?
Yeah, so that's a very good question. I talk about more on the underlying technology. Building a business definitely means a lot of meeting those business requirements. And going back to the model here, there are a few things we've put in. So for example, data governance. Right, like that's a very good place to put it into the source connector. Once the data come into the system, it must adhere to a schema or like some constraints. So you can easily, when you configure in our term, the streams, you can put in those policies there, and the system will automatically enforce those policies and send alerts. So that's basically where we think the streams will enforce all the policies. Thank you.
I have my own question, if I may. Being a host, I can ask any type of question. So it's somewhere along the lines with what the gentleman asked about monetization. But what about kind of like a measuring and providing, if you're in a business of moving data, you might provide different SLAs. How fast you can move like terabytes from their data center to the place where they can do fast querying and stuff like that. Have you experienced this type of problems to solve, and how this, like maybe technical, how this business requirement will end up as a kind of like engineering problem to solve? Including SLAs, doing the measuring or monitoring, kind of have a understanding how fast things are moving or how slow.
So that's a very good question, and it's a very challenging problem to solve, I have to admit. So wearing my engineering hats, the way I negotiate with people is you can't expect anything, like everything from us in terms of SLA. It has to be constrained, right? Like if your data volume is always under some threshold and the transformation is, we'll talk about in terms of like small, medium, large complexity. So like with different metrics, we'll figure out what kind of resource you need to run the job. If everything stays within the threshold, then we can guarantee the latency. What we can guarantee about SLA is the uptime. But of course, when you have a lot of data volume and within the resource, there could be back pressures. So latency is a much harder SLA to meet. So for any latency requirement, it has to be constrained with the set of like the rules that we set.